Hello, everyone, and welcome to this event that we are very proud to have today, where we will be presenting the new destinations available for PhD candidates willing to experience a mobility period in the US and Canada, thanks to the collaboration that we have with ISSNAF. And we're very proud of this collaboration, which is long dated, has a long tradition, but has been made institutional back in May through an agreement that was signed between ISSNAF and Politecnico di Torino. And I'm very proud to welcome today Dr. Zufada, ISSNAF President, Professor Salleo, Chair for the International Affairs for ISSNAF, and which is they are now sitting overseas. And on this side of the ocean, I'm very happy to introduce you to Professor Brusa, the director of the PhD School of Politecnico, and Professor Romano, who is in charge, is an ISSNAF member, and he is also in charge of the relationship with ISSNAF at this time. So we're here today to offer an overview of all the possible opportunities that are being offered by ISSNAF for the next month's, next semester, very likely, to all the students or the PhD students who are interested into this. So I am very pleased again to welcome everyone and to give the floor to Dr. Zufada, ISSNAF President, for a welcoming word and an introduction about the event and the next speakers, who, by the way, will be all ISSNAF members and will favor and facilitate the collaborations between Politecnico and the United States. Thank you very much. Dr. Zufada, the floor is yours.
Thank you, Professor Verga. And I wish to thank Politecnico di Torino for your desire to collaborate with ISSNAF and the participants here who are interested to hear about what we have to offer. First, I want to say a few words about who we are. We are the Italian Scientists and Scholars in North America Foundation. It's a non-profit foundation that this year celebrates its 15th birthday, and it gathers more than 3,000 members who are Italian expats who have been raised and educated in Italy and then have moved and worked and have spent their professional life in North America. We are distributed all over the territory, and we are active in research organizations and development, and we are interested in cultivating this community as a network. And as a network to leverage off one another and celebrate the achievements of the Italian community in North America. We are also very interested in helping the newer generations, those who are newly arrived to North America, and also people in Italy, because we do believe that as a resource, we can be helpful to research in Italy. And many of us are very interested in giving back to Italy. It is in this spirit that we have actively sought a collaboration with the Politecnico of Torino. And the goal of this relationship is to give access to doctoral students to research organizations in North America for a period where students will work in our laboratories, guided or assisted by PIs in our laboratory, often, but not necessarily exclusively, Italian researchers, members of ISSNAF. And we want to do that with the intent of forming long-term collaborations with the Politecnico. In other words, It's not solely a touch and go of the students. We would like the students to come back to Italy, having brought the additional know-how and having brought it into the research group at Politecnico. And therefore, this will promote better collaboration and an acceleration and an expansion of the research capacity of Italy, which we think we can help. And it is with this intent that we are here tonight to let you know what specifically we have to offer. Without any further ado, I'm happy to give the floor to Professor Alberto Salleo, who will be then introducing all of the opportunities that we have prepared for you. Thank you all.
Thank you, Cinzia. My name is Alberto Salleo. I am very excited to get this program started. As Cinzia said, one of the intents is to create long-term collaborations, and therefore we have selected hosts quite carefully with this intent. And we span East Coast to West Coast and the Midwest, North and South, so there is a lot of variety. We span different disciplines in engineering and science, and so we're hoping that there will be good matches for all our hosts. In terms of universities, we go from Duke, Purdue, Cornell, Stanford, Berkeley, Princeton, and Caltech. So as you can see, these are really the excellent universities in the US, and we're spanning 3 time zones in the US, so our hosts are in a variety of time zones. I am actually on the West Coast, so it's currently 8:20 a.m. for me. Before we get started, maybe a couple of housekeeping items. Not all our hosts were able to be here today this morning. So for those that aren't able to be here, I have either a brief synopsis of the research that I will present myself, or they sent videos that I will play. And we will actually start with the hosts that aren't able to be here. That way, when you have questions, the hosts that are here will be able to answer those questions. And in terms of questions, please put them in the Q&A, not in the chat. I saw a few questions already showing up in the chat. Please put them in the Q&A, and I will moderate them to the best that I can at the end of the webinar. So these are the housekeeping items. So let's start with the presentation of our hosts, and I will start with a video from Professor Marco Bernardi at Caltech. Just give me a second to share video.
Hello, this is Marco Bernardi. My group at Caltech works on theory and computational physics of materials. We use quantum mechanics and computational methods to study novel materials. In particular, we use a family of methods that are called first principles because they take the structure of the material as the only input, and without using any information from experiment, these methods aim to make quantitatively accurate predictions of materials' properties. Now, you may have heard of density functional theory, which is a widely used first principles method to predict bonding in materials. For us, density functional theory is the starting point to develop more advanced, perturbative, and many-body methods to study solids. My group in particular develops and applies new method, and one of our main focuses is understanding how electrons interact and move inside materials. Roughly, I could divide the work in my group into 3 parts. 1, we develop methods to compute the interactions between electrons, spin, phonons, defects, and other excitations, focusing on the solid state. 2, we apply these methods to study 2 main problems. 1, transport phenomena, in particular focusing on predicting conductivities and understanding different transport regimes in different classes of materials. 2, studying materials excited out of equilibrium, where the goal here is both to understand the ultra-fast dynamics of the excited electrons and atomic vibrations, and also to use this information to interpret ultra-fast spectroscopy measurements, for example, using pump probe and time domain diffraction techniques. My group also develops a code that is an open source code that we released a couple of years ago, and that now has hundreds of users and aims to make these methods broadly available to the community. To give you a couple of examples, so for transport studies, we focus on two regimes. One is over a wide temperature range near room temperature. Transport is limited by the atomic vibrations or phonons. When the electron-phonon interactions are weak, we use the Boltzmann transport equation, doing calculations that are entirely parameter-free. And with this method, we can accurately predict the transport properties of a wide range of semiconductors, oxides, and organics, and other materials. When the electron-phonon interactions are stronger, which is a broadly relevant scenario in many oxides, we have developed many body methods, in particular relying on the cumulant and Green-Kubo approximations. And with these methods, we can study systems where the mobility is relatively low and the strong coupling and the polaron effects govern the carrier dynamics. Finally, at low temperature and in doped materials where the role of defects and impurities is dominant, we have developed approaches, still based on density functional theory, to capture the scattering mechanisms between the charge carriers and the defects, and with those we can make accurate predictions of charge transport as a function of dopant and impurity concentration. These methods form a very broad toolkit to study transport phenomena in the solid state. For studies of ultra-fast dynamics, we time-step the Boltzmann transport equation that allows us to obtain the time-dependent populations of excited electrons and phonons. This gives us access to a wide range of information. For example, with these methods, we've been able to predict the different dynamics of electrons and hole carriers out of equilibrium in various families of semiconductors, and also predict the related spectroscopic signals for this phenomena, as well as the ultra-fast structural dynamics. Just to show you an example of a topic that recently got us very excited, we have developed an approach to predict spin relaxation due to phonons, which is a problem that is broadly relevant to quantum technologies, for example, spin qubits. With this method that relies on a Dyson equation for the spin vertex function, we can make accurate predictions of spin relaxation times in semiconductors, as well as access a range of microscopic information about the spins that interact strongly with the phonons. As I've mentioned to you, we developed open source code, and this code is called Perturbo, and it encompasses a range of methods to predict transport properties, ultra-fast dynamics in very wide classes of materials that range from simple systems to magnetic materials and materials with spin-orbit coupling or enharmonic phonons and so on. This code is very efficient, and there's at least a few members of my group that devote a fraction of their time to maintain, improve, and continue expanding this code. I will leave you here with a brief summary, and I will highlight that next year I will have 1 or 2 openings to work on a range of new topics, in particular decoherence in solid-state qubits, as well as studies of correlated quantum materials using many-body methods, but we're also trying to expand toward machine learning methods, and other types of simulations for quantum circuits. Unfortunately, I was not able to be here today, but if you have any questions, please feel free to reach out to me, or I hope that you will have a chance to talk to some of my group members during your visit. Thank you.
So this was Professor Bernardi. He is located at Caltech. For those of you who don't know, Caltech is in the Los Angeles metropolitan area. This is a video he prepared for the incoming Caltech students, which explains the references at the end towards openings, but everything else is accurate. And I encourage everyone to get in touch with potential hosts if you're interested. So next now, we will go to another host who wasn't able to be here today. Just give me a second. Okay. So our next host is located at Princeton University. Princeton University is a classic Ivy League university located on the East Coast in the US. As you can see on the map, it's pretty much halfway in New Jersey between New York City and Philadelphia. Princeton is a primarily undergraduate institution. It has about 8,600 undergraduate students and about 3,000 graduate students. Our host in Princeton is Professor Amilcare Porporato. Professor Porporato is a professor in civil and environmental engineering at Princeton University, and his main interest is hydrogeology. He has quite an interdisciplinary research group with research areas spanning water, climate, and energy, hydrogeology and the atmospheric environment, but also chemistry, biology, and technology, especially as they relate to the soil and microorganisms. You can go on his website to find more details, and again, get in touch with Professor Porporato if you're interested in his research. His research interests are described quite well on his website. I just underline a few aspects here. He's focused on quantitative description and predictions, and in particular, he's interested in the water cycle, and he describes himself as an eco-hydrologist. And in particular, he looks at he looks at moisture, microbes, plant dynamics, and a mathematical modeling of biogeochemical cycles. And he's interested in semi-arid ecosystems. His research methods are really interdisciplinary. So he has fluid mechanics, statistical physics, nonlinear dynamics, non-equilibrium thermodynamics, plant physiology, and you can read all the details on his website. So a really broad research group, very interested in sustainability. If you're interested in working with Professor Porporato, please get in touch with him. He'll be happy to consider an application. Another host that wasn't able to be here today is Professor Lanzara. Just give me a second. Just a second, I don't know what's going on. Okay. Professor Lanzara is a professor at the University of California, Berkeley. For those of you who don't know where Berkeley is located, it's in the San Francisco Bay, and you can see there is on the east part of the bay. So it's about 10 miles away from San Francisco, in the proximity of multiple national labs. Professor Lanzara is a solid state physicist. She works in the physics department, but she really does materials physics. In particular, she's interested in the physics of correlated materials, so oxides that have correlated electrons, superconductors. But lately, she's also been interested in graphene and layered semiconductors, such as transition methyl dichalcogenides. She does all sorts of measurements. In particular, she develops experimental tools to study the electronic structure of these materials, and her specialty is angle resolved photoemission spectroscopy, or ARPIS, and different declination of ARPIS, which she performs at national labs. So if you're interested in this type of fundamental materials research, get in touch with Professor Lanzara. You have her email address there, and you can look at her website, where she has more details on her research. Okay, so our next host is actually a video, but the host is here in person, although a bit jet lagged. So we will play the video, but if you have questions, Professor Scovazzi will be able to answer those questions as he's here live. Give me a second, I'm running into the same problem as before. I guess after 2 years of COVID, I still haven't mastered the use of Zoom. Okay.
Buongiorno, sono Guglielmo Scovazzi from Duke University e sono impiegato nel Dipartimento di Ingegneria Civile e Ambientale nella stessa università. Mi scuso innanzitutto perché non riesco a essere presente di persona. Purtroppo sono in viaggio per lavoro durante il meeting e avrei voluto esserci. Questa è Duke University più o meno oggi. Duke si trova nella Carolina del Nord, a Durham, che è una città non tanto distante da Washington, circa un po' meno di un'ora di volo. Le statistiche di Duke possono essere riassunte in questo modo. Ci sono 10 scuole, tra le quali quella di ingegneria, 11 istituti, circa 6.800 studenti di laurea, circa 10.000 studenti di postlaurea, 2 premi Nobel. Ci sono 4 dipartimenti nella scuola di ingegneria: biomedica, civile e ambientale, ingegneria elettrica del computer, meccanica e scienze del materiale. Abbiamo circa 124 faculty, professori che sono tenure track, 1200 studenti di laurea, circa 600 studenti di dottorato. Volevo fare un breve riassunto della mia esperienza accademica. Ho conseguito la laurea al Politecnico di Torino in ingegneria aerospaziale nel 1998, nel 2004 il dottorato in ingegneria meccanica a Stanford University. Dal 2004 al 2012 sono stato Senior Researcher a Sandia National Laboratories, che è la ex divisione di ingegneria di Los Alamos ed è stata trasformata in un laboratorio separato. Nel 2012 ho fatto ingresso a Duke come professore, dove adesso sono ordinario, cioè full professor in ingegneria civile. Nel mio lavoro io mi occupo di meccanica computazionale, cioè lo sviluppo di algoritmi per la risoluzione di problemi di meccanica classica governati da equazioni alle derivate parziali. Le applicazioni sono in ingegneria civile, meccanica, aerospaziale, biomedica, anche in geomeccanica e in ingegneria ambientale. A me interessa sviluppare algoritmi per classi di problemi, cioè la progettazione di algoritmi. Allego qui alcuni sponsor della ricerca che hanno finanziato gli sviluppi nel mio gruppo. Ultimamente uno degli argomenti che sono più interessanti nel mio gruppo di ricerca sono lo sviluppo di algoritmi per problemi con geometrie molto complesse. Questo deriva dal fatto che il connubio di ottimizzazione topologica e additive manufacturing produrranno forme geometriche sempre più complesse di quelle che attualmente risolviamo. Allora, normalmente quando uno risolve problemi di calcolo computazionale si parte da una certa realtà, si crea un modello geometrico CAD, da questo si ricava una griglia di calcolo e su questa griglia viene impostato un metodo numerico, per esempio gli elementi finiti, per effettuare il calcolo. Il problema è che la generazione del CAD e della griglia possono richiedere l'80-90% del tempo di analisi. Quindi il nostro obiettivo nel mio gruppo è di cercare di passare dalla realtà al calcolo molto più velocemente di così. E lo otteniamo con un nuovo metodo che abbiamo sviluppato che si basa sul concetto di immersione delle geometrie in griglie di calcolo direttamente e approssimazioni delle geometrie. Si parte da una realtà, si creano delle realtà, delle geometrie approssimate su cui si calcola molto rapidamente la soluzione e poi si riesce anche a ricostruire la geometria sulla base della risoluzione della griglia. Abbiamo applicato questo metodo appunto ai problemi di ingegneria biomedica che facevo presente all'inizio e abbiamo anche applicazioni in geomeccanica, meccanica dei fluidi, cioè CFD, in cui dimostriamo che questi metodi sono molto più veloci dei metodi tradizionali, per cui un'analisi che costa magari 2 settimane a farsi, nel nostro caso riusciamo a effettuarla in minuti o ore. Abbiamo anche applicazioni in meccanica della frattura. In termini di potenziale collaborazione, chiaramente a noi interessano la collaborazione con gruppi che sviluppano algoritmi di ottimizzazione topologica, gruppi interessati a modelli ridotti, in generale gruppi che vogliono anche sperimentare la simulazione diretta su modelli che vengono da immagini o scansioni. L'idea è quella di sviluppare un'alternativa ai modelli CAD attuali che sia più facilmente integrabili con l'intelligenza artificiale, digital twin, data-driven computing e design. Ovviamente sono aperto a nuove idee, per cui questi sono soltanto alcuni argomenti di potenziale collaborazione, ce ne potrebbero essere altri. Grazie.
Okay, and just as a reminder, Professor Scovazzi is actually here live for questions. Before I give the floor to our next host, who will be Professor Pavone from Stanford, I see a recurring question in the Q&A, so I want to answer it right away, whether the mobility is open only to Italians, and it's not. It's open to students of Politecnico, of course, provided that they can get a visa to come here, because we're always subject to US immigration rules. So that is a caveat over which we have no control. Okay, so now Professor Pavone, just give me a second. Okay, Marco, the floor is yours.
Great, thanks. Should I speak in Italian or in English?
Go with English, and when you need me to change, just say next, and I will click through.
Sure, great. All right. Good morning, everyone. At least it's a morning here in California. My name is Marco Pavone, and I'm a professor at Stanford in the Department of Aeronautics and Astronautics. I studied in Italy, and then after my laureate, I moved to Boston, where I did my PhD at MIT in the field of robotics and autonomous systems. And then after my PhD, I worked for 2 years at the NASA Jet Propulsion Lab, where I had the pleasure to interact with Dr. Cinzia Zuffada, who is here in the call. And then since 2012, I've been a professor at Stanford. And currently, I'm on a partial leave of absence from Stanford, as I'm serving as director of autonomous vehicle research at NVIDIA, which is one of the main AI companies out there. Next. So my work is essentially in the field of autonomous systems, such as self-driving cars, unmanned aerial vehicles, autonomous spacecraft, autonomous robots in general. And in particular, in my lab, we focus on the design of planning and decision-making algorithms for autonomous systems. That is, we focus on developing techniques, borrowing tools from machine learning, optimal control, and optimization to allow the robots to make decisions on their own. Think of a self-driving car that is interacting with humans, like pedestrians or bikers. Then the car needs to understand the environment, and based on that understanding, has to make decisions that strike a trade-off between safety and efficiency. And we look at different aspects of robot autonomy. We look at algorithms for agile motion planning. So basically, we look at algorithms that allow an autonomous robot to maneuver at the limit of its dynamical envelope, at the limit of what is actually possible. Think of maneuvers that are very fast, very agile. Of course, controlling autonomous system is difficult because there are a lot of uncertainties. Uncertainties in the reconstructional environment, in the case of self-driving cars, uncertainties in terms of what humans will do in the future. And so we do quite a bit of work on the topic of uncertainty propagation and calibration. We try to understand how uncertainty affecting different functions in the autonomy stack of an autonomous robot are going to eventually impact decision-making. And then we find ways to mitigate these uncertainties in order to promote safety. Third, an important topic in my lab is represented by assured autonomy, that is safety guarantees for those components in the brain of an autonomous robot that are based on machine learning. As many of you may already know, machine learning has been revolutionizing the way we design autonomous robots. But machine learning also presents new challenges. In particular, it's very difficult to provide safety assurances or safety guarantees for machine learning components. And this is a problem because in many cases, the autonomous robots are safety critical systems. For example, a self-driving car, if there is an accident, someone might get injured. So we would like to endow machine learning components with the same type of safety guarantees and safety assurances that we do have for more traditional components not based on machine learning. So that's what we're working on quite extensively. Fourth component of the research agenda is represented by algorithms that allow a robot to safely interact with the humans. This basically entails designing algorithms that allow a robot to forecast what a human will be doing, say, in the next 3 to 5 seconds. And then based on this forecast, we design algorithms that can compute actions that anticipate possible reactions from the humans around the robot. And finally, at a more system level, from a more system level point of view, we're working on system level coordination algorithms. So assume that now you have multiple autonomous robots, for example, a fleet of self-driving cars. What is the best way to coordinate them in order to achieve a given task? For example, in the case of self-driving cars, we want to optimize throughput within a transportation network. Next. So yeah, most of our work is on the design of algorithms, but we do apply our algorithms on a variety of testbeds and experimental platforms. So on the top left, I'm showing a video from the International Space Station, where we tested on a platform developed by NASA Ames called the Astrobee. Some algorithms we developed in my lab that allow the Astrobee to manipulate, to grasp and manipulate objects in space. So for example, here you see the yellow robot, which is the Astrobee. that is using our algorithms to attach itself to one of the walls of the International Space Station. Top right, together with NASA, we are developing new robotic concepts to explore extreme terrains on other planets, in this case, exploring caves on Mars. Bottom left, at Stanford, I'm the director for the Center for Automotive Research at Stanford, where we have 4 full-scale self-driving cars that we use to experiment a variety of different robot autonomy algorithms, from trajectory forecasting algorithms to decision-making to perception. And on the bottom right, we also do some work on the quadrotors. So for example, here you see one of my former students that is fencing with one of the quadrotors. And as you can see, the quadrotor is outsmarting the student and is not hit by the sword. We are open to collaborations on any of these projects. I will just put, and this is my last slide, a little bit of emphasis on one of the main projects right now in my lab. That is a project funded by NASA on the topic of safe AI for future aviation. So this is related to what I already said. So this project, which is a very large project that entails collaboration with a number of other institutions such as MIT, Berkeley, Georgia Tech, and also companies and research centers such as Raytheon Technology and Lincoln Labs. So here the goal is to design and provide safety assurances for machine learning models in the autonomy stack through designing algorithms to verify the safety of a machine learning component, algorithms for fault detection, isolation, and recovery. So once we have deployed the brain of basically the autonomy stack on the robot, and the robot is moving around, we want to monitor that the robot is doing the right thing. And this is difficult to do with machine learning components in the loop, and that's what we are working on as a second thrust. And finally, we are looking at the algorithms that allow to coordinate AI-driven agents in a safe fashion. So I'll stop it here, and if there are any questions, I'll be happy to address them.
Thank you, Marco. Marco might not be here during the Q&A session live, but you can, of course, always get in touch with him if you have questions about his research. Okay, our next host will be Professor Bertino from Purdue University.
Okay, good morning and good afternoon to everyone. Very pleased to be here. Purdue is one of the largest universities in the Midwest. It is located in Indiana, 2 hours south of Chicago and 1 hour north of Indianapolis. By the way, Chicago is a very nice city. I like it much better than New York. Okay, Purdue was founded in 1869. And is a major technical university. The major colleges are the College of Agriculture, the College of Engineering, the College of Science, and the College of Veterinary Medicine. I want to mention that in particular, a lot of astronauts graduated from Purdue. You can see in my slides, actually Armstrong, who graduated from Purdue. And we have a big building, the Aeronautic and Astronautic Building, which is named after Armstrong. I am in the computer science department, which is in the College of Science. Engineering as the College of Computer Engineering and Electrical Engineering. The computer science department is quite large. Currently, we are 78 faculty, and we are poised to grow over 100 faculty in computer sciences. Also, Purdue hosts one of the largest cybersecurity centers, the Sirius Center, and this was one reason why I moved to Purdue in 2004. Before that, I was a professoressa ordinaria at the University of Milan for 10 years, and before that at the University of Genoa for 3 years. My research area is cybersecurity, and in our department, we have over 15 faculties working on different areas of cybersecurity. So if you like this topic, you have to come to Purdue. So next slide, please. I've been working in cybersecurity for more than, I would say, 30 years. on many different areas. Two recent important areas are the security and privacy of cellular networks. Those are cellular networks are today critical infrastructure, and therefore the security is critical. But those protocols are very complex, very complicated, and it's not easy to find mistakes in the design of those protocols. So about 4 years ago, we started a project which actually got a lot of visibility. So we came up with a methodology to analyze those protocols. And basically, this methodology combines formal methods that we have in computer sciences, namely model checking and symbolic execution techniques, with protocols for the verification of cryptographic protocols and test beds. Basically, using our methodology, we were able to show that we shown 10 new attacks that had been uncovered so far. And we reported them to the 3GPP standard bodies, which is in charge of standardizing those protocols. After that, we have continued with many other techniques, extended this initial work. This work has also been of high interest to companies. I have collaborated and still collaborating with Intel because companies are very interested in systematic approaches. Recently, we have been extending those methodologies to the use of machine learning techniques. And we have actually developing this work as a part of a big AI institute funded by NSF. I am one of the co-PI, and this AI institute focuses on the security of edge computing, including therefore the cellular network protocols. Next slide, please. My other current important area is the one of the software security. Unfortunately, software still is always very insecure. So we have come up with various techniques which combine typically static analysis techniques with the machine learning to find the vulnerabilities, bugs in the software. And again, we, for example, have developed a technique in which we could automatically analyze more than 1,200 applications to find the vulnerabilities, for example, in the use of a one-time password, in the use of random generation of random token. A notable result, very recent, has been that we found in Linux kernel, which is a huge open source project, 40 new bugs, which had been there for 15 years. And nobody had discovered them. For this, we combined natural language processing techniques with static analysis. So we have plenty of projects in those areas, and I'll stop here.
Thank you, Professor Bertino. And now actually we'll try an experiment. Our next host will try presenting from his own computer, and that's Professor Curtarolo from Duke University.
Can you hear me?
All good.
Okay, perfect. Thank you very much, and I appreciate the opportunity to change my slide at the last minute. I had some news. So okay, so I want to thank my other collaborator. Sorry, my other collaborator from Duke University, Professor Scovazzi, for having introduced Duke University. It's located in North Carolina, has almost 7,000 undergraduates and 10,000 graduate students, plus 2,000 postdocs. Is very research oriented. Okay, so you see that the ratio between research and education is very high into research. Okay, what about me? My name is Stefano. I was born in Venice. I studied in Padua. I studied electrical engineering first, and then condensed matter physics second. And then I went to MIT and for my PhD, and then I remain in the United States. Okay, you can see my websites. You can take a picture and feel free to look more about what we do. My research is theoretical. I am a computational thermodynamist and computational electronic structures, and we use a massive amount of computers. We practically use like 500 million computer hours per year, which is pretty much most of the public part of the DoD supercomputers. And our research is sponsored by DoD, by NASA, and by DOE. Okay, we have a lot of openings for students and postdocs, etc., and internship. Our student needs to be able to come to United States, okay, so through the visa, but also to achieve a DoD background checks to use the computers. We have a lot of success with Europeans and the people from Far Asia. What do I study? I study disorder. Okay, many years ago we realized that the disorder was giving some unexpected properties, and disorder is all about what you get with respect to what you mix. Think about that: you mix a bunch of blue atoms and white atoms, and then you expect to get azure. This is not what you get. Actually, you get red. You get something that is completely unexpected. And the trick is to find when do materials mix and what you get. Okay. So about when the materials mix, we developed the code and an algorithms after many years. And in 2014, we developed this expansion, which called partial occupation, which is pretty much an expansion of disorder. You consider disorder as an expansion in order tiles on which you do a Gibbs probability, and you get all the ensemble properties. This was published many years ago. Then after that, we applied to oxides. Oxides was the big challenge, and then we discovered a new classes of oxide, entropy stabilized oxide, which actually right now they're used for catalysis, thermochemical water splitting, and coating, and so on. And one of my former students now is Professor John Hopkins. Is doing thermochemical water splitting. We apply the same idea to carbides, okay, because we started receiving funding to study super high temperature materials, and we discover a new class of systems, which is high hardness, high entropy metal carbides. If you are a thermodynamist like me, you know that there is tungsten carbide, titanium carbide, etc. But if you mix a tungsten, hafnium, zirconium with carbon, you get some extra properties, increase the melting point, you can increase hardness, and you can also change some electrical properties. And we discovered these classes of materials that have a melting point above 4,000 kelvins. So we also have we collaborate with experimentalists, and you can see that there are also issues about melting these objects and measuring the melting point. Okay, so then we started doing research in hypersonics with the previous high hardness systems. We have addressed the issues of the structural issues. We know how to bond these materials, making grading of different metals. So we have a part of the wings and part of the jet engines that are pretty much have a smooth transition of metals. Okay, this is a funded Muri that I'm leading, and we already discovered super hard materials with more than 40 GPa of hardness. Then we have tackling thermal issues. We write our own code, and we discover when the effect of vibrations of these super high temperature carbides, and when we have thermal expansions or we don't have thermal expansions, because when you have these objects, then you need to deal with gigantic thermal stresses, so you need to tackle this. And we soon we're going to receive funding to study plasticity in disorder alloys, where we have postulated some phenomena, and we need to write a code to see if it happens. Then we have issues about radiative issues. This is actually an article that came out today. It's in Nature Communication. This is plasmonic high entropy carbides. You know, plasmonic is optical electrical interactions, and people use plasmonic system up to 500-600 Celsius. Well, guess what? They do exist up to 4,000 Kelvin, and we found that we have experiments of hafnium tantalum carbide up to 1,500 Kelvin. This is incredibly important, because if you do layers of a plasmonic high entropy carbides, you can do what are called a hyperbolic.
Looks like we have lost Professor Curtarolo. Okay. All right, so while we try to get him back, why don't we move to Professor Monticone at Cornell.
Okay, and Alberto, I think you have my slides.
Oh, sorry, I'm running into always the same problem. Just give me a second.
No problem.
Okay, all yours.
All right. Hello, everyone. It's a pleasure to be here, at least virtually. And just a brief introduction about myself and Cornell University. My name is Francesco Monticone. I studied at Politecnico of Torino, and I've been in the US now about 10 years. I studied in UT Austin in Texas, and now I'm an assistant professor at Cornell University. I've been at Cornell for about 5 years now. So Cornell is we are located in a beautiful campus, as you can see in the photos here, in a beautiful area between in New York State, approximately halfway between New York City and Toronto, actually a little closer to Toronto, Canada. And Cornell is a member of the Ivy League, which is a group of elite universities in the Northeast of the United States, together with Harvard, Yale, Princeton, and a few others. Cornell is a pretty big school. We have 15,000 undergraduate students, 10,000 graduate students, and almost 2,000 faculty members. Following the vision of our founder, Ezra Cornell, he wanted to establish an institution where any person can find instruction in any study. And that is reflected in the huge number of colleges, schools, departments, and courses you can take at Cornell. At Cornell, you can take courses from advanced string theory to wine tasting. By the way, wine tasting is the most popular course we have at Cornell right now. The College of Engineering itself has 14 departments with probably around several hundreds faculty members in total. And another interesting number, there have been 50 Nobel laureates affiliated with Cornell University as faculty members or alumni over the past 150 years. Next. Okay, so what do we do at Cornell? So my group works in different areas in applied electromagnetics, metamaterials and metasurfaces, and theoretical and computational nanophotonics. Now, just to give you an idea, very general description of what my group does, our goal is to better understand the fundamental and practical limits of electromagnetic wave manipulation and how to approach or even bypass them using novel designs, novel concepts, and engineered materials and so-called metamaterials. Next. Okay, just a visual representation of my research portfolio. As I said, we study fundamental limits based on very general considerations that have to do with causality, energy conservation, passivity, stability, and how these general concepts apply to electromagnetics and photonic systems. And then we investigate complex wave interactions with engineered artificial materials, what we call metamaterials, and also the two-dimensional versions of metamaterials, which are called metasurfaces, and nanostructures, plasmonic systems. Professor Curtarolo was talking about plasmonics, and that's something we also work on. And then more exotic systems like non-reciprocal, topological, and time-varying systems. And all of this for many applications in different areas, from the idea of potentially creating ultra-thin imaging systems to invisibility devices, how to make an object invisible, and several projects about energy and sustainability that I've been working on recently, from wireless power transfer to passive radiative cooling. And I have projects in pretty much all of these areas that are active right now. But in this presentation, I would like to highlight 2 specific projects. So if you can go to the next slide. So project 1 is related to the topic of metasurfaces, which is one of the most active areas of research today in optics and photonics and technology in general. Now, the general vision of this field is to be able to replace bulky conventional optical elements, for example, a conventional lens, with very thin devices, what we call a metasurface, which are based on wave interactions with arrays of nanostructures. And through the interaction with these nanostructures, it's possible to create an optical system that is able to do the same job of a conventional lens or even more advanced functionalities over a very thin, very small thickness. And specifically, this project is theoretical and computational, but with plenty of interactions with many experimental groups we are actively collaborating with. And specifically, the student intern will assist my PhD students and postdocs in the design and simulation of novel ultra-thin metasurface devices for focusing and imaging. And essentially, the ultimate goal would be to create a paper-thin camera or a paper-thin telescope, or in general, very, very thin optical systems. Next, another project I would like to highlight is much more theoretical. In this project, the student intern will assist, again, my PhD students, postdocs, and collaborators in the development of a general theory of the fundamental bandwidth limits of how wave interacts with materials and devices. And this follows some of the recent work we have been doing using general principles, for example, causality, and how the principle of causality affects the optical properties, the response function of an optical or electromagnetic system. Based on these ideas, we were able to find ultimate limits, fundamental limits on things like high refractive index materials, achromatic metalenses, and also invisibility devices, answering questions such as to what extent you can make an object invisible and over what bandwidth. So is it possible to create an invisibility device that works for all colors, for example? And specifically, the intern will work on helping us in this ongoing work, developing this general theory, but also on a specific application example of this general framework for fundamental limits. Next, just very briefly, I would like to just mention the required background for the two projects, and any projects in my group. I expect that you have taken courses on electromagnetic fields, optics and photonics, and then specifically for project 1, you should also have some prior experience with analytical modeling and numerical modeling and simulations in electromagnetic and photonics, and some prior experience with computational imaging would be a plus, but not necessary. For project 2, you should also have solid background in complex analysis and linear algebra, and the prior experience with convex optimization would be a plus, but again, it's not necessary. Finally, I would like to mention that to make meaningful contributions to these projects, the internship should last at least 6 months. But in any case, the ultimate goal of this collaboration would be to build the foundations for continuous interactions with faculty members and PhD students at Politecnico on some of the most advanced foundational and emerging areas of photonics and applied electromagnetics. And that's all I got. So if you have questions, let me know. Thanks.
Thank you, Professor Monticone. We actually have Professor Curtarolo back online, so we will go back.
Sorry, network problems. 1 second. If I can share the screen, I recap.
Are you allowed to share the screen?
1 second. No, I was disabled participant share screen.
Okay, why don't I share mine since I have your presentation?
Yes, please.
It's not the latest one, but
okay. My apologies, some network problems.
Sorry. Okay.
Okay, page 4. Okay.
Okay. Yeah,
so, thank you. Okay, so for hardness, we have addressed the problems. We have a Muri, which I'm leading, and we're already finding composite of titanium carbide and titanium nitrides that have a hardness higher than 40 GPa. Then we are studying thermal issues. As you know, that there are at this temperature, there are there are problems of vibrations and thermal expansions. So soon we're going to have a funding to understand plasticity in disorder systems, and we're going to have to write a code and check if some arguments that we postulated do exist. Then the last but not least, probably one of the most important part is the radiative issues. As you know, that if you increase the temperature, you have a black body radiations, and therefore we calculate the radiations, and we want to change the radiation spectrum, moving some of the ultraviolets to the infrared, and therefore we are creating and understanding metamaterials of these high temperature carbides, and to generate what is called a hyperbolic system and change the Planckian radiation. And this is just this plasmonic entropy carbides is an article that came out today and in Nature Communication, and we are showing that you can have plasmonic up to practically 4,000 Kelvin, well above what the people are using, which is 600 Celsius right now. Okay, next slide, please. This is actually is a dream to have a system that are both amorphous, which means that are geometrically in a disorder position, and chemically disorder. So you would get the best of two worlds. High entropy glasses, metallic glasses, and wherefore here you can see that we are developing the code to study the configuration of the systems. And once you have these codes, you can calculate properties as a function of the disorder of the amorphous disorder, and create spectral descriptors. For here in the case of glasses, we had only energy, but we wanted to do the spectral descriptors also for hardness and so on. Okay, next slide. And now it's the end. Okay, well, sorry, this was the fix. If you want to know more about my work, we wrote two reviews about high entropy ceramics, and one about machine learning for alloys, and then actually a very short review that is materials research, MRS Material Research Bulletin, about how disorder can help ceramics. We are open to internship students and postdocs. You know where to find me. I sent the link of my PowerPoint to the chat. Feel free to download it. What we want from the students, it's not a matter of commitment time. Is more like understanding that science is really a life mission, is not a job. We spend a lot of time, we spend a lot of effort, but you really need to like what you're doing, because otherwise we will not succeed. Okay, so this is what we want: successful students, so that they can make science a part of their life career. And thank you very much. And again, sorry for the network problems. Thank you.
Thank you, Professor Curtarolo. I also want to remind everyone, if you have questions, post them in the Q&A section. And then last is going to be actually me. Let me see if I can do it right this time. Okay, so my name is Alberto Salleo. I'm in the Department of Material Science and Engineering, and I'm currently also the chairman of the department. A few words about Stanford University. Stanford is located in the Bay Area, but in the southern part of the Bay. You can see here where it's located compared to San Francisco. We're a very large campus with not so many students and beautiful views. So we're located in the heart of Silicon Valley. We have about 7,500 undergraduate students. So you can compare that to Cornell. We're slightly smaller than Cornell, and about 8,500 graduate students. So we, just like Cornell, we have very broad education offerings, all the way from classics and arts to the med school, but we're really known for our engineering school. The university has 7 schools in total, and we have proximity to 3 national labs. SLAC is just about 1.5 miles up the road, and I'll talk about more about SLAC later. Lawrence Livermore National Lab and LBL are all within 30 to 40 miles. The School of Engineering, so as one of the 7 schools, has 9 departments, and the Department of Material Science is one of those 9 departments. We have about 21 active faculty, and about 170 PhD students. So you can see that we're very research heavy given the number of PhD students. We have about 85 postdocs currently. So my group actually is culturally, we're sort of a fundamental structural property group in materials, and we work with soft materials, but over time, we've really started spanning from fundamentals all the way to devices, because we study fundamentals because we're interested in properties, and then we want to see what those properties do, and the best way to see what a property does is to put it in a device and study the behavior of the device. So we start from the very basic characterization, and we use X-ray diffraction, spectroscopy, and transmission electron microscopy to understand the structure of the polymers that we work with. And we work with polymers that are electronically active, also known as conjugated polymers. We have developed a full fabrication protocol to be able to make devices with these polymers so that we can observe what they do in very controlled ways, so that we have devices that have very well-defined geometries. This include photolithography, soft matter processing, and printing. We then study the functional properties of these materials in the devices. We're particularly interested in terms of properties in charge transport, because we want to use these polymers in electronic devices, but also ionic transport. Lately, we've been interested in more electrochemical devices. And then we also look at photocurrent, because we have some work in solar cells. From there, once we have the properties, we try to understand the device physics. Device physics is heavily influenced by the design of the device, but also the materials properties. And that's a combination of measurements and modeling, so that the model can help us interpret the measurement and extract materials properties. And then eventually, thanks to our fabrication methods, we're able to make small demonstrators. We don't go all the way to circuits. It's typically single devices or small amounts of single devices. So this could be an array of artificial synapses shown there, or also wearable sensors. We have an effort in wearable devices lately. So what are the things we're interested in for students to come and visit us? So we do characterization of these polymers as they're being used, and in particular, we have developed synchrotron-based X-ray diffraction of electrochemically active polymers as they're being electrochemically modified. So this involved the design of a holder, custom holder, and then we go at the synchrotron and we get beam time. So a student who's here for long enough time would be able to actually experience beam time. It's relatively easy to get trained to take data, and then, of course, there's a data analysis, which takes quite a bit of time. But we're also interested in transmission electron microscopy. We use different types of transmission electron microscopy. What I'm showing here is a type of microscopy that's based on scanning nanodiffraction. So you condense the beam down and you collect the diffraction pattern and you scan it, and the collection of diffraction patterns, so the collection of reciprocal space images, allows you to build the real space image. We also do more traditional high resolution TM by phase contrast. Now, what do we get out of these measurements? So in synchrotron X-ray diffraction, what you can see here is as we change the potential of a film compared to a reference electrode, that's the CV curve that's shown on the left, we can actually see the diffraction peaks coming in and out of diffraction. So we can literally see what happens to the structure of the polymer as the ions that are driven by the potential from the electrolyte into the film, they expand the lattice parameters and so on. And that allows us to then, as we measure electronic transport at the same time, to figure out how the presence of ions affects electronic transport. The type of devices that is interesting in is batteries, supercapacitors, but also what we call electrochemical transistors, which are used in sensors. In terms of transmission electron microscopy, we reconstruct the microstructure of the polymer. The lines here are not single polymer chains. You can't really see those by transmission electron microscopy. They're the directions of the crystals made by these polymers. But then we work with theorists that, based on these crystal directions, are able to reconstruct, they're polymer physicists, they're able to reconstruct the position of and the conformation of each chain. And then from there, we run transport models, and so we can tell where the charges go through this microstructure, and this allows us to determine what defects are particularly detrimental to electronic transport as you think of using these materials for example, transistors or solar cells. And the idea is that once you know what defects are detrimental, you can imagine processing conditions that will minimize those defects, and you gain a fundamental understanding of how these materials work. In terms of polymer-based devices, we have a wide range of them. So we work with what we call biohybrid sensors. This is actually in collaboration with a group at Cornell and Cambridge, where they essentially put cell walls on top of our polymer devices. And what this allows us to see by measuring the impedance of that device, for example, we're able to electronically monitor virus fusion. Other types of biosensors actually are more classical redox sensors. So you have a redox reaction that reveals the presence of an analyte. And here what we've done is we couple actually the sensor directly with an amplifier, and these are all made with polymers, so they can all be made on flexible substrates. And this allows us to get an amplification of the signal up to several orders of magnitude. So we have sort of a sensor and amplifier all integrated in one, all made with polymers. And then another line of research that we've had for a few years now is to make artificial synapses. So these are essentially analog non-volatile memories, and you can see we can tune the conductance of these analog non-volatile memories very linearly. And you could use these for what are called hardware accelerators. So to run matrix operations very fast at very low energy, essentially using the laws of physics, Kirchhoff's law and Ohm's law. Now, what I'd be interested here is we can make the single devices, we understand them quite well, but I'm interested in seeing whether students would be excited about making arrays, since we have microfabrication ability, making arrays of these devices. And it's sort of a fundamental aspect of microelectronics research that arrays of devices can do something much more powerful than what a single device can do. And so here is really the creativity of the student, given sort of the infrastructure that we can offer, to come up with ideas of what an array of these sensors can do. And maybe, for example, if you have an array of artificial synapses, can you demonstrate some ability to accelerate computing and matrix multiplication in hardware? So this is all I had for my research group. Again, if you're interested, shoot me an email. My contact information is easy to find on the internet. So let's see, it's probably now a good time to move to the Q&A. I see there's one in the Q&A box, and this is probably more for Professors Brusa and Verga, whether co-tutela students would be able to avail themselves of this opportunity.
Yes, thank you very much. So, good evening or good morning, depending on the side you are. Actually, the co-tutela agreement obviously is one of our goals, but we have to consider that in practice, we have to negotiate together with each university the contents and the possibility to set up an agreement and the co-tutela, depending on the rules and the regulations which are applied to each PhD program, and also to the point of view of the fees. So from the point of view of the activity, we will work together, ISSNAF and the PhD school, to make it possible. But on the other side, obviously, we have to take care of the position and the different rules of the universities.
There's also another question in the chat, whether there are opportunities in the field of Industry 4.0, 5.0, smart intelligent manufacturing, robotics, IoT for manufacturing and related fields. Of the present hosts, so maybe Marco Pavone would have been a good person to answer that, but I'm wondering whether Professor Scovazzi has any answer to that question. You're muted.
We may have to connect to some colleagues within Duke, I think, but I personally don't work in Industry 4.0 the way we typically understand it at Politecnico di Torino.
Yeah, I don't either, but I'll turn that question to Professor Pavone, and we can see if he has an answer about here at Stanford. I don't know, Francesco, if you know anyone at Cornell who works in that area.
Not really. I would have to think about it, probably in some different departments. Smart intelligent manufacturing, robotics. I mean, it's pretty broad.
Yeah. I should add that the goal of this program is really to connect with the hosts that that presented today. So if you're interested in that topic, you should write to the hosts directly. And if they work in that area, they would be the prime contacts. At this point, we really would like this program to be limited to the hosts that were here today. And then another question about the duration of the mobility. I don't know that we set a fixed number of months. It has to be a long enough time to have an impact on the research group that hosts, but also to build a connection. So I think 12 months is probably a minimum, and I think we talked about all the way up to 18, if I remember correctly.
And I mentioned the 6 months in my presentation, but yeah, 6 months is really short. So if it is 12 months, I think that's the right minimum time to make a meaningful contribution to any advanced project.
Yeah, I agree. Any soft robotic research opportunities? Let's see, anyone in the group that is currently still here doing soft robotics? So in my group, we don't really do soft robotics, but we work with soft materials that could be used in soft robotics. So this would be the case if a student has a good idea. I could be the primary advisor at Stanford, and I would also find a collaborator within Stanford that would handle more the soft robotics part, but the project would have to be centered within my group. So I'm happy if a student is interested and has an idea to see whether that's possible, since we make sensors that are suitable for soft robotics. And we've been talking to soft robotics group, but haven't had really any active collaboration. This would be the case where, for example, the student could be the person that starts an active collaboration, which would be new for me, for another faculty here, and for someone at Politecnico. So that's certainly a possibility.
This is Cinzia. Sorry for jumping in. It would be advisable for the students who are preparing an application to sort of write what they are actually interested in. Here I see a list of disciplines, right? But there is no specificity as to the project. So I would recommend that somebody who did not find what they wanted to hear at today's presentation might elaborate a little bit better on what they wish to have. And certainly we will make an effort amongst the hosts that were at the presentation today to better understand whether their wish can be accommodated.
Yes, thank you, Cinzia. I saw a question about how to apply, and I will ask our colleagues at Politecnico to answer that. But before we get to that, one aspect that will be important in the evaluation is the fit with the host. So as Dr. Zuffada said, it's a good idea to start thinking in terms that are a little bit more concrete, and maybe get in touch with the host you're interested in to really see if there is a good match, or maybe build a good match together. That really increases the chances of success, because in the end, you'll get evaluated by how well you fit into your hosting research group, because that really is going to be the hallmark of success. So in terms of how to apply, Professor Brusa or Verga, if you could address that.
Yes, actually, we consider that the opportunity to move requires a sort of an internal call in our university. So let's say that in a couple of weeks, we set up a sort of a call for participants open to all the PhD candidates, but particularly to women that are performing the first and the second year, because if they are already the third year, which is the last one in Italy, probably there is not enough time to set up the mobility and to conclude this kind of activity with this opportunity. But the idea is to open first to the proposed activities which were presented today, and towards the universities which are receiving in practice according to the topics which were presented and proposed. But for sure, we can open a specific window on the proposal of our PhD candidates in such a way that we can agree eventually together with ISSNAF whether we are able to find additional hosts and eventually other departments and research groups in which the topics which are proposed and the specific programs, as Dr. Zofada told us, could be set up. So let's say that we'll proceed in a couple of weeks. You will monitor our web page of the PhD school, but for sure, since in the middle we'll have also the council of the school will suggest to your coordinators of the PhD programs to set up also this kind of screening inside each PhD program, also together with your supervisors.
And we'll wait maybe just a couple more minutes. We're coming, well, we just passed 9:30, so we're getting close to the end, but I'll wait just maybe for one last question if it comes. Doesn't look like it. So maybe I'll pass the mic to Professor Brusa or Professor Verga for closing remarks. Thank you everyone for coming.
Thank you very much, Umberto. First of all, I have to write in capital letters, thank you all of the members of ISSNAF, and particularly to Dr. Fada, Professor Saleo, and but the Directors Board in general, because you are creating a real gate towards the North America. But let me say that is also a gate towards the future of our PhD candidates in terms of job placement, but also in terms of growing up in topics and experiences which are very fruitful for their future. And let me say that in our conception of our school, for sure, the PhD school is where we set up our educational path, but simultaneously we organize the research activities together with our departments and the specialized centers we have in our technical university. But for sure is also a community, and is a very wide community in which we have young researchers as the PhD candidates are, the senior researchers and professor, but generally speaking, all the staff of our technical university working together. And this opportunity, which is offered by ISSNAF, is also the opportunity to enlarge this community and to give a sort of international dimension of our community, which is not only scientific, but is also an educational community. So the opportunity given to our PhD students is extremely interesting, because is towards to have them growing up as much as possible as conscious researchers and innovators. From this point of view, we'll open this camp, this kind of a call for the applications, let's say within a couple of weeks, as I already told you. And in particular, this will be open, as Professor Saleo already told us, to all our PhD candidates. The only point which is important to remember, as we already mentioned, is that depending on the nationality and the requirements and the restrictions which are applied, by each government, the possibility to assess and to have this kind of opportunity obviously depends also on the possibility to get visa. But in our principle, obviously, all the PhD candidates working within our PhD programs are welcome to apply for this kind of opportunity. And for sure, we'll try to set up also the co-tutel agreement together with the hosting university, although generally speaking, it's not so simple because the regulations, in particular in the United States, with respect to our regulations are quite different. But nevertheless, together with your mentors in the ISSNAF, we try to make it work and to have a strong effort in this direction as much as possible to set up also the co-tutel to have the opportunity to get the award in PhD also in the hosting university. We are sure that this collaboration will improve our impact, which is the dominant word which is used by our rector to promote the activity of our university, but for sure is a very nice opportunity, in particular for the young people to open mind, to have another experience, and in particular to learn very strategic applications and topics of science and technology. So from this point of view, we're extremely grateful to all of you in particular, but in particular in general also to the foundation, because this is the tool, let me say, the most appropriate tool to promote the growing up of our PhD candidates. But to say goodbye, I leave the floor to Marcello Romano, our colleague. Is aware about the two communities because he's coming from ISSNAF. He spent several years in the United States, but simultaneously now he is our professor in aeronautics and aerospace engineering. So from this point of view, I think that he is the right person to take the contact and to wish to express the best wishes to our PhD candidates to take the nice or the better exploitation we can from this point of collaboration and from the agreement.
Thank you very much, Professor Brusa, and good evening and good morning to everybody. And I'm very happy that we are at this point. Finally, after a lot of efforts, this is the real starting point for making this collaboration a reality. And I totally agree with Professor Brusa in his view of the importance of this. Yes, for Politecnico di Torino and for ISSNAF, but especially for the young people that have this incredible opportunity in their PhD years here at Politecnico to visit and to interact with the esteemed colleagues that have presented their research work, and having lived a similar experience now 23 years ago, I can say that basically it changed my life. The possibility to, during my PhD at Politecnico di Milano, in that case, to spend 6 months, even just 6 months at the research university in US, and then yes, coming back to finish the PhD, and then going back to US and then back to Italy. So it's, I believe, also a way to foster what hopefully could become also a two-way movement between North America and Italy that could be advantageous for basically both entities, both sides of the Atlantic. So with this, I give back the floor to Professor Brusa.
Okay, thank you. Thank you very much, Professor Romano. Thank you to everyone participating today, and especially to our colleagues from overseas, our colleagues from ISSNAF. And really thank you for the opportunity to host our students and more in general to promote this cooperation between you and Politecnico di Torino and our colleagues from Politecnico di Torino. Thank you to Professor Brusa, who was always very open and supportive to this initiative. And we're very happy that this is the starting point for a new way of collaborating from which our students will possibly benefit intensely. I did myself part of my PhD in the United States, and it was a very wonderful, real wonderful opportunity and experiences. So I wish that really many students will take this opportunity. Once more, thank you. Thank you for being connected with us. Thank you to all the participants. And well, we're still available, of course, through our emails for other questions that may arise. You can contact the PhD school, and we will provide you with all the information needed. Thank you so much. Have a good day overseas and good night on this side of the world. Bye-bye.
Bye-bye.
Bye. Thank you.
Bye.
Thank you all.
Thank you. Bye-bye.